All right, so I am going to preface this lesson with A, most students hate it. B, the ones who hate it because they didn't pay attention the first time and thought, I know how to do this. I can do it my own way. And usually what happens is after 2 or 3 days of figuring out that they can't do it their own way, they then have to relearn the correct way. So if you can at least be patient with me, I do solemnly swear that there is a best way to do these problems, and this is it. Might you sometimes be able to get the right answer doing it another way? Sure. However, if you would like a method that will work reliably and consistently and efficiently, this is it. In 1999, NASA's Mars Climate Orbiter, designed to monitor the red planet's atmosphere, was lost in space because engineers failed to make a simple conversion from English units to metric units. Maybe this mistake could have been avoided if the engineers had remembered their dimensional analysis skills. In this lesson, you will learn to convert among different units of measure using dimensional analysis. A measurement is not complete without appropriate units. Using dimensional analysis of units may have prevented the loss of the $125 million spacecraft in 1999. Yes, the people in Houston did not talk to the people in Florida about the metric use of centimeters and meters and converting it to feet and inches, and we lost it. Yes, up in space, it's gone. We never found it again. So, the big race. Leslie rode at a rate of 2 meters every second. However, you want to know how fast she was going in feet per second. Work with your team to determine Leslie's rate in feet per second. Refer to the math notes box in this lesson for equivalent units of measure. So if you need units of measure, they are also in your agenda. So we're looking at 2 meters per second. And we're looking to convert this to feet per second. So we need some conversion facts. This is where that concept of the big one, the giant one, came in. We want to multiply by things that are worth 1. So I know that there are 100 centimeters in a meter. So I'm going to multiply by the fact that there are 100 centimeters in 1 meter. Now, I wrote this fact this way on purpose. I put the meters on bottom and the centimeters on top so that I would be able to cancel out the meters. I did not put the 1 meter on top because then the meters wouldn't have canceled. But I do know that 100 centimeters is equal to 1 meter, making this fraction worth 1 whole because the numerator is the same as the denominator. I'm then going to multiply by the fact that every 1 inch is 2.54 centimeters. So 1 inch is equal to 2.54 centimeters. And now, because I put the centimeters on bottom, I can cancel the centimeters. So this is the whole purpose of dimensional analysis, is making sure that we are very purposeful in the way that we put things into the fractions. So now I only have seconds left and inches left, but I really didn't want inches and seconds. I wanted feet per second. So I also need a conversion for how many inches are in a foot. And on purpose, I'm going to put the fact that there are 12 inches on the bottom so that I can put the 1 foot on top, canceling the inches. So all of my units have canceled except for feet on the top, seconds on the bottom. That was my goal. I'm going to multiply across the top, 2 times 100 times 1 times 1. Oh, before I do that, I can actually simplify one thing. I have a 2 in the numerator and a 12 in the denominator. 2 divided by 2 is 1, and 12 divided by 2 is 6. That saves me from having to simplify the final answer. So 1, 100, 1, 1. If I multiply across the top, I get 100 feet per. And if I multiply across the bottom, 1 times 2.54 times 6, I get 15.24 seconds on the bottom. Now, this is not feet per second. This is 100 feet per 15.24 seconds. I would actually divide the numerator by the denominator in order to get that it is 6.6 approximately feet per second. And that would be my final answer for unit rate. So the dimensional analysis is all of this part where we are multiplying by fractions that are worth 1. So if we go back, basically what we did was we multiplied by 1, and then we multiplied by 1, and then we multiplied by 1. We didn't actually change the value of the initial rate. So this rate, 2 meters per second, is equal to this rate because all we did was multiply by 1s. But each of those 1s had to be a conversion, that there's 100 centimeters in a meter, that every 1 inch has 2.54 centimeters, that 1 foot has 12 inches, and that we purposefully put meters diagonal from meters. So one was in the numerator and one was in the denominator. Same thing with centimeters, one in the numerator, one in the denominator. Same with inches, one in the numerator, one in the denominator. Now, if you write it down and all of a sudden you go, oh no, I put 12 inches over 1 foot, this isn't going to work. All you do is erase it and flip it over. It's still worth 1 because the numerator and the denominator are equal lengths. All right, a snail's race. Terry, Madeline, Matt, and Olivia were working on a different rate problem. They were preparing for the county fair snail race and knew their species of snail could travel up to 8 feet per hour. The snail race lasts only a few minutes, so they want to know how many inches their snail could travel in 1 minute. Madeline spoke up. I know there's 12 inches in a foot and 60 minutes in an hour, but I always get mixed up about when we're supposed to divide and when we're supposed to multiply. Help! Olivia chimed in. Do you think we can try using ratios so that we remember when to multiply and when to divide? Let's list out everything we know. So what do they know? We've got, there's 12 inches in a foot, there's 60 minutes in an hour, 8 feet per hour, data that we're collecting. Madeline exclaims, I got it, and shares her work with the group. How did Madeline compute 96 inches per hour? So the original was 8 feet per hour, and then she multiplied by 12 inches per foot. So she was able to cancel the feet and the foot, which even though they're not the same word, they mean the same thing. So you can do 8 times 12, which is 96, and we still have inches. 1 times 1, and we still have hours. And so we end up with 96 inches per hour. She multiplied feet per hour by inches per foot, which only left her with inches per hour. I think you're onto something, Madeline. We know that 1 foot is equal to 12 inches, so we can make a giant 1 out of this ratio. Since we already know that multiplying by a giant 1 does not change the value, let's multiply the snail's rate of 8 feet per hour by the giant 1, and showed her work. Hey, that's cool, said Matt. Now we can rearrange like we did before. So you'll notice that the feet and the 1 foot, that's what cancels. That makes its own kind of giant 1. That's why you're allowed to rearrange it. And he arranged it, and he's allowed to do that because of the commutative property that says you're allowed to change the order when it's all multiplication. Terry is concerned because they only know the snail's pace in inches per hour when they need to know the pace in inches per minute for the race. What is the snail's pace in inches per minute? So we're going to go 96 inches per hour times the fact that every 1 hour has 60 minutes. Now, this is your giant 1, that 1 hour has 60 minutes. And I put minutes on the bottom and hours on the top so that the hours would cancel. Hours on the numerator, hours on the denominator cancel. And we end up with 96 over 60. And this is inches and this is minutes. And then we would actually divide the 96 by the 60. So what's happening in here is 96 divided by 60, and we get approximately 1.6 inches per minute. Or you can go over here and say 1.6 inches per minute. All right. So we're going to go on to the back, which is, obviously more of the dimensional analysis. And here we go. Back to the big race. Now that the team has practiced dimensional analysis from the snail's race, they want to convert Kristen's rate in the big race from 2 meters every 5 seconds to inches per second. They wrote down the following fraction multiplication problem, but we're struggling to make giant 1s. Okay, so 2 meters per second. That's your original fact. That's up here. That's her speed. 100 centimeters in every 1 meter. So that works, right? That would cancel the meters, and there is in fact 100 centimeters in every 1 meter. And then she wrote 2.54 centimeters in 1 inch, which is also true. However, when she wrote that second one, nothing canceled. And what she would have liked is for the centimeters to cancel. So this one needs to be the reciprocal. All right, needs to be the reciprocal. They should have flipped it over, which is what I had said on the front. So it should be 2 meters per 5 seconds times 100 centimeters in every meter times the fact that 1 inch has 2.54 centimeters. So now meters and meters cancel, centimeters and centimeters cancel. And you can look around and see, 5 and 100, 5 goes into 5 once, and 5 goes into 100 20 times. So I could simplify that. And then I would just multiply across the top for 40 inches, multiply across the bottom 2.54, and I've got seconds left over down there. But that's not a unit rate. I would actually have to do 40 divided by 2.54, and I would get approximately 15.7 inches per second. All right, help the team fix the mistake and solve the problem. So that's what we just did. We fixed the mistake was that this one, when they plugged it in, it is a giant one, but it was upside down. And because we were using 2 decimal places in the 2.54, when we went to get our final answer and we did 40 divided by 2.54, it says in here, use the same number of decimal places in your answer. So we were using something that had 2 digits, so our answer should have 2 digits. So we would want to go with approximately 15.75 inches per second. And that's what they're talking about with precision. On the printed notes, I have approximately 16 inches per second. But if we want to make sure that we use the same decimal places, there was 2 decimal places in the work, which means I left my answer also with 2 decimal places. Physical quantities are measured in units, inches, grams, and hours. A dimension is the broader concept, such as length, mass, and time. For example, one of the dimensions for the 1999 Mars orbiter was height. Height was measured in units of meters. So the dimension was height, and it was measured in meters for the units. Another dimension is mass. The launch mass of the Mars orbiter in 1999 was 338 kilograms. What was the launch mass of the Mars orbiter in pounds? So notice this time we don't have a rate. We have 1 unit of kilograms, and we're converting it to a different unit, pounds. So when we start, we're going to start with a fraction, but we don't have anything for the denominator, so we just put it over 1. And now we can multiply by those giant ones. We can multiply by those conversion facts, and we have something down here in the denominator to multiply by. So the first thing I want to get to grams instead of kilograms. So I know that there's 1,000 grams in a kilogram, which would allow me to cancel the kilograms. And I did have to look this one up, that every 1 pound has approximately 453.59 grams. And so number 1, our answer is going to be approximate. But I can also cancel the grams, and all I have left now is pounds. And because you were going from kilograms to pounds, you shouldn't have any units left in the denominator. That's a good thing. So multiply across the top, you get 338,000 pounds over the 453.59, and you're going to divide. So I'm going to divide 338,000 by 453.59, and I'm going to get approximately 745.17 pounds. And I went to the 2 places because the problem had another number that went to 2 places. If you were just going to report, you'd be like, oh, it's about 745 pounds if you're just chatting with someone. Last question. A leaky faucet drips 1 fluid ounce of water every 5 minutes. How many gallons of water will it leak in a year? So there's a lot of conversions. This is one of those problems where you would never be able to keep track of whether you multiply or you divide, whether or not you've done all of the conversions necessary, unless you're writing them down. So first thing we're going to write is 1 ounce every 5 minutes. And our goal is to get to gallons in a year. So I need to decide, do I want to tackle the ounces first or do I want to tackle the minutes first? And most people go with the minutes because it's time and we're more familiar. The ounces is actually a little faster, but let's go with minutes. Most people say minutes. So first I know that there are 60 minutes in 1 hour. I also know that there are 24 hours in 1 day. I'm trying to work my way up to a year, and I'm going to use 365 days in a year. And so I've got minutes and minutes that cancel. I've got hours and hours that cancel. I've got days and days that cancel. And now I've got ounces per year. I'm going to continue, and I can continue all in one long multiplication. Now I'm trying to get rid of ounces and get to gallons. So the ounce conversion that I know is that there are 8 ounces, and notice I put it on the bottom so that it'll cancel, in every 1 cup. I also know that there are 4 cups, which I put on the bottom, in every 1 quart, and did that on purpose. And then I'm going to put that there are 4 quarts in 1 gallon. So now I can cancel cups and cups. I can cancel quarts and quarts. And if I look back at the very beginning, I can cancel ounces and ounces. So that's a lot. No one's keeping that all in their head. No one's dividing that all out on their calculator one step at a time in order to get all the way there. But I do know that I only have gallons left on the top, which is what I was looking for. And I only have years left on the bottom, which is what I was looking for. I'm also going to look to see if there's any simplifying. If I have a calculator, guys, there's no reason to do any of this simplifying. But if you're in a test or quiz and you don't have one, or you just happen to not have a calculator, the simplifying will make your life a lot easier. I'm going to simplify 5 divided by 5 is 1, and 60 divided by 5 is 12. I also notice that I've got a 12 here and a 4. So 4 divided by 4 is 1, and 12 divided by 4 is 3. These ones, nothing's going to happen to them because they're ones. Nothing can simplify. Sometimes I go over them so that I know that they don't need to be touched or looked at again. I can also see, though, that there's a 24 and an 8. So 8 divided by 8 is 1, and 24 divided by 8 is 3. And the only thing I have left in the denominator is 4. And of the things I have left in the numerator, none of them are even. So that's as far as I can go. I'm going to use a calculator more than likely, but I'm going to multiply all the numbers that are left on the top and get 3,285 gallons on the top. And along the bottom, the only thing I have besides a 1 is a 4, so 4 years on the bottom. And when I divide those, I'm going to get 821.25 gallons per year. Or you could go with approximately 821 gallons per year if you were looking to round. You will notice that on the numbers in our list of work, nothing up there had a decimal. So it would be perfectly acceptable to either leave an exact answer or estimate it to a whole number, since everything on the top was a whole number. So now that you are all dimensional analysis experts, I may actually, if I can find a few extra videos or samples on this, I may plop those in as well besides my videos. This is not something you're going to master overnight. It takes practice, and it takes a lot of foresight, where you're sort of looking ahead and saying, where do I want to get to and how do I get there? So it takes a lot of practice. This is definitely one that you want to be doing lots of these questions live with me, asking questions as you go, trying them ahead of time and seeing which ones you can do on your own and which ones are too long and you need a little bit of extra direction. So I will see you in class. Bye.